Half-Life 3? Confirmed? Okay, so let's talk about half-lives in the world of nuclear physics. So, imagine that we have some number of particles or molecules of a certain element. Over time, that element can begin to decay, or those particles of that element can begin to decay. But they're not all going to decay at once. Some of them might decay early, some of them might decay last. So let's write this. The change in the number of particles in some amount of time is equal to some negative lambda multiplied by n. Where this lambda here, we refer to this as a decay constant. We refer to this delta n over delta t, this entire term, as the activity. And this n we have here, this is like the initial quantity. It's what we have. Now, why is this important? Well, this activity is telling us in general how many particles are undergoing some decay. And it's dependent on some decay constant and how many particles you have. As you can imagine, if you had more stuff, you could have more opportunities for something to decay. Statistically, everything works out in terms of the ratios being the same, as we'll see, and possibly in the next video when we talk about graphing this. But we just have more things there. So if we actually look at this, though, we might notice that this starts to look kind of like a differential equation, where if these delta symbols that we wrote here were actually turned into derivatives like dn and dt, well, that's definitely a differential equation. So let's take a look at this. Let's bring our initial quantity n down, and let's bring dt up, so that we get the following. Delta n, or as I'll simply write it, dn over n equals minus lambda delta t, which is some small change in time. That negative is there is because we're losing particles. Some of these particles are decaying. If you've been following around with your calc classes or doing a bunch of weird stuff with us, we quickly see that these are integrated, and we're going to integrate them from 0, some initial point in time, to some time t later. Okay, so if we integrate this from some 0 to t, what we quickly see here is that on this right side, we're just going to have, given that this negative lambda is a constant, we're just going to have negative lambda t. On our left side, we're technically integrating this from some 0 time to later time, but what we really mean by that is some n naught, the initial quantity, to some n of t, some number of the quantity that we have at some later point in time. And if you recall from your calculus course, dx over x, or dn over n, is a special integral. It's actually the natural log. And when we take the natural log of this, we're going to take the natural log of the upper minus lower boundaries. So this would be like the natural log of n of t minus the natural log of n naught. And we subtract the logs. What we actually get, due to log rules, is n of t over n naught. So that's a nice little log rule to remember there. We're just doing upper minus lower, but then log rules come in and we divide instead. Now to get rid of that log, we exponentiate e to each side. The natural logs die out. So we have n of t over that initial quantity, which we're calling n naught, equals e to the minus lambda t. And then to simply actually find n of t, we just move n naught over to the other side, and we call it a day. And this is a nice half-life derivation. Now, we can actually take this derivation a little bit further, because this derivation here will give us the number of particles at any point in time. The true half-life derivation is telling us how long it will take so that only half of our particles remain in their original state. So how long does it take for half of them to decay is another way of thinking about that. So here's what we can do here. We can take this and we can write it as the following. If we want the number of particles that we have left over to be half of the original for a true half-life, then we can rewrite this as follows. We can say n naught, the original amount, divided by 2, or half of them. This is equal to n naught e to the minus lambda t. Now why does this matter? Well, the n naughts go away here. Very, very nice. And what we end up having here is a 1/2 equals e to the minus lambda t. Now here's a kind of nifty move here. This is a 1/2, but this is an e to the minus lambda over t, which can also be written as 1 over e to the lambda t. This means if we reciprocate both sides, we flip them up, we'll get the following. 2 equals e lambda t. That's a little math trick right there. If you didn't know what you were doing, maybe you thought that you just forgot to put the 1 over, and maybe you forgot to write the negative, but we actually reciprocated both sides. Now, if we wanted to solve for t, we could do it as follows. To get rid of this e here, we'll take the natural log of both sides. The natural log and the e's are going to wipe out, so we're going to have now is the natural log of 2 equals lambda t, and then simply dividing each side by lambda, we find t here. This means that the amount of time it takes for us to decay some number of some molecules by half, and I wrote this rather large of t 1/2, but this is really just saying like a half-life here, the time it takes to decay by a half, is equal to the natural log of 2 divided by a decay constant. This pops up so often that while we can write it as t or t 1/2, we could also write it as tau. Not to be confused with torque. Torque is a vector. This half-life time, tau, is the amount of time it takes for some number of particles to decay down to half as many as before. Okay, so with this in mind, what we can also do is we can use this equation to figure out how long it's going to take to get us to a percentage. So let's pretend that we want to say, hey, I've got 80% or 0.8 of the original amount. How long would that take? Well, using this idea, we can say 0.8 n naught of n naught e to the minus lambda t. This gets rid of the n naughts again, which is very nice. And then what we're quickly able to do, just moving some things around, is we can say that the natural log of 0.8 here divided by negative lambda is going to equal that amount of time. Natural log got rid of the e, brought the negative lambda under, just like before. So in general, if you're looking for a percent of the original quantity, you can put that percentage in here. And this will give you the amount of time it takes to get down to that percentage. Okay? Another way of thinking about this then, because you know the natural log of 2 over lambda is going to give you the half-life time, you can actually work this out mathematically on your own as an exercise for the viewer, that you could also write this as negative tau, and then the natural log of that percentage there. Okay? So that's another way of kind of solving this out. So I just like to use this, though. I'm often given decay constants, which is nice. But if you're not given a decay constant, if you're given a half-life time there, you can use that instead. In our next video, we'll look at how to read a half-life graph. But for now, we're finished. I gotta go get the door. Adios.